Okay, we are going to learn about carboxylic acids, yeah, and their derivatives. Okay, so when we look at carboxylic acid, okay, so we know that, okay, when we look at acidity, okay, we know that carboxylic acid is a weak acid. So what weak acid will do? Yeah, weak acid generally they are going to actually react, okay, with base, okay, to form salt and water. Yeah. So what do you get if, let's say, for example, if I ask you a question, what do you get when ethanoic acid is a weak acid, okay, reacting with sodium hydroxide? So if I write the equation, this is going to be ethanoic acid and I react with sodium hydroxide, I will get CH3COO minus, okay, this one, and then an A plus and water. This is what they mean by the salt, okay, and then they are going to give you water. So the salt is going to be sodium ethanoate. Yeah, it's an ethanoate salt. So because if you have ethanoic acid, so you get ethanoate ion. So this is going to be sodium ethanoate. And this salt, okay, this salt is going to be, yeah, basically the formula you can see, it will follow CH3, C double bond O, O minus. Okay, so this is going to be known as ethanoic. Okay, if you have methanoic acid, then you are going to get this particular salt, O minus. Okay, this is H. Yeah, this is methanoate. Okay, if you have propanoate, okay, you are going to get, okay, this one, okay, you are going to get this. Yeah, so this one you adjust accordingly. Okay, therefore, okay, we know that carboxylic acids, okay, because they are going to be partially dissociated in water, yeah, they are weak acid. Okay, and the position of the equilibrium, yeah, always, okay, when they are weak acid, the position of the equilibrium is always lies to the left. Because why? Because they don't have tendency to dissociate. Yeah, so they are going to be on the left. Okay, but okay, we have learned, okay, we have learned that we learn about phenol, we have learned about water, we have learned about ethanol. Now we are going to bring in, okay, we are going to bring in carboxylic acid. So now if I ask you to arrange this according to the acidity, yeah, according to acidity, do remember, okay, all these phenol, water, ethanol, carboxylic acid, they are all weak acids. Yeah, they are all weak acid. But by definition, when it comes to weak acid, yeah, you see the one that has acid, yeah, so which is going to be carboxylic acid, should be the most acidic compared to all of them. Yeah, so carboxylic acid is going to be kind of a better acid among all the other like phenol, water, and ethanol. Okay, that will put it at position number 1. Okay, what is position number 2? We have learned, okay, that phenol, yeah, phenol C6H5OH, okay, they will give you C6H5O minus plus H plus, okay, which is going to be your phenoxide ion. Okay, a phenoxide ion, they are going to be more stable. Remember, they are more stable. Why? There is going to be overlap of the lone pair of electron with the benzene ring, yeah, making it more stable. Another way to look at it is the charges, the negative charges is going to be equally distributed within the benzene ring. So what will happen is the negative charge is not going to be, the density of the negative charge is not going to be at the oxygen atom over there. Therefore, okay, the combination of the H plus and the phenoxide ion, they tend not to combine a lot. So it means that the backward reaction is not favored. So they are going to form more, yeah, more forward reaction, which is going to produce more H plus. Okay, this one we have learned. Okay, that makes phenol, okay, to come at position number 2. Okay, and water is going to be position number 3. Ethanol is going to be position number 4. Why ethanol is at position number 4? Ethanol is C2H5OH. They will give you C2H5O minus plus H plus. Okay, this is going to be known as ethoxide ion. This ethoxide ion, okay, what happens? Okay, C2H5 is an electron donating group. When they donate the electron, okay, the charge density of the negative charge at the oxygen atom is going to increase. What it will actually make, okay, there will be more reaction between the H plus and the ethoxide ion. That will make the reaction to go more, okay, towards this side. Yeah, so it will not form this. Okay, so it will not form C2H5O minus, or it will not form so much of H plus. That will decrease the H plus, okay, making it to become less acidic. Okay, so that explains, okay, the position. So if you want to arrange the strength of the acidity of the following, okay, your ethanoic acid will actually come at position number 1. Okay, phenol will come at position number 2. Water will come at position number 3. Ethanol will come at position number 4. Okay, and if you look at the value of the pKa, remember, pKa value lower is going to tell us that something similar like pH. Yeah, so which is going to be is a better weak acid. So if you look over here, this is a better weak acid, okay, compared to phenol, compared to water, compared to ethanol. Yeah, so that is the value of pKa. Okay, the lowest pKa is going to tell that this is going to be a better weak acid. But do remember, okay, one thing that you need to remember, because of this arrangement, okay, carboxylic acid is a better acid. So therefore, okay, they can react with, let's say, for example, sodium. Okay, they can react with sodium hydroxide. Okay, but if you compare, okay, like phenol also, they can react with sodium, they can react with sodium hydroxide. Okay, but if you look at ethanol, okay, and water, water can react with sodium, okay, but water cannot react with sodium hydroxide already. Yeah, and then ethanol, okay, they can react with sodium, okay, but no reaction with sodium hydroxide also, okay, because they are not strong enough, okay, to react with sodium hydroxide. That is going to be the explanation, what I try to relate with ethanol and phenol. Now you can actually see how it is taking place for carboxylic acid. Okay, if you look at more in detail, okay, if you look at the structure of carboxylic acid, C double bond O, and then you have O and H. Okay, if you put it like this, like for example, the OH bond, okay, the OH bond, if I actually put it in this form, the OH bond, okay, is weakened by the carbonyl group. Yeah, the carbonyl group, what they do, yeah, carbonyl group is the oxygen over here, the double bond oxygen. The electrons in the CO bond, okay, are drawn towards the C double bond O. Yeah, it means that this is the electron towards the CO bond. They are going to be drawn towards here. Okay, they are going to be drawn towards the C double bond O. Okay, so basically here, that's why they actually put it. They are going to, the electron will go here. Okay, so because the electron is moving, it's going to go towards here. Okay, it's going to move towards there. So electrons are drawn away from the OH bond. Okay, so when the electrons are drawn away from the OH bond, okay, what will happen? Yeah, what will happen? Remember, I told you, you can look at it in form of stabilization. Yeah, or you can actually see in form of whether they can break or not. Yeah, so here you see the explanation here. The carboxylate ion, what is carboxylate ion? Okay, let's say for example RC double bond OOH. Okay, when they change into RC double bond OO minus, okay, this is going to be known as carboxylate ion. Okay, carboxylate ion. Now, the carboxylate ion, yeah, is stabilized by the delocalization of electron, okay, around the COO minus group. It means that, okay, you are going to actually delocalize. The electrons are going to be delocalized from here to here. Okay, so it's like something like benzene, but now they are going to actually get delocalized from oxygen atom between carbon atom and another oxygen atom. So it's around here. Okay, they become delocalized. They can move around here. Okay, when they can move around, so it means they are going to become stable. Okay, they're going to become stable. So it's going to be stabilized. Okay, this delocalization is good. Yeah, why? Because they are going to, same thing, yeah, the phenoxide, they are going to spread out, okay, the negative charge, okay, of the carboxylate ion. Okay, remember the two things that we learned under the phenoxide. Yeah, one, okay, the negative charge is spread out. Okay, what does it mean? This density, charge density, or the negative charge at that O is less. Okay, what will happen when the charge density is less over there? Yeah, they are going to actually, okay, you see, it is reducing the charge density, making it less likely to bond with the H plus. Yeah, so it means that they are not going to be bonded so much with this. Okay, they are not going to be bonded so much with this. So what does it indicate? Okay, it just simply indicates that they cannot go over there. Okay, so it indicates that they want to form this. Okay, they want to form this. So because of that, you are going to get a lot of H plus. Okay, that's why it's highly acidic. Okay, compared to the rest. Okay, compared to the rest, even compared to phenol. Yeah, even compared to the phenol. Okay, it's going to be more acidic. Okay, and the stability, yeah, the stability, when you look at carboxylate ion, if you compare the stability of carboxylate ion and phenoxide ion, carboxylate ion is more stable. Okay, carboxylate ion is more stable. Okay, therefore, okay, this is going to make, okay, the carboxylic acid to become a good dissociating weak acid. Yeah, a good dissociating weak acid. So that is the same. Yeah, it's the same as phenoxide ion. Yeah, if you can understand what I taught you about phenoxide, okay, you definitely can understand what is over here. Okay, the only thing that is different over here now is, okay, the electrons, okay, are going to be attracted towards the O over here. So they are going to go from here to here. Okay, so when they go from here to there, okay, what does it mean? Okay, there is going to be a delocalization of the electron between this over here. So something similar to phenol, okay, something similar to phenoxide, but now, yeah, they are going to be not going to be in circle, but they are going to be around, the electrons become delocalized between oxygen, carbon, and oxygen over there. Yeah, so they move around. Okay, so that is going to be making it, if they ask you, okay, what makes the acidity of carboxylic acid, yeah, discuss about it, then you need to explain based on that. Yeah, the next part over here, okay, is going to be, we know that, okay, we know that chlorine, yeah, chlorine is an electron withdrawing group. Yeah, we know it's an electron withdrawing group. Now we are going to actually look at, if let's say I have chlorine added. Okay, if I have chlorine added in a molecule, okay, what will happen? Yeah, what will happen to the acidity? Yeah, so if you look at ethanoic acid, yeah, if you look at ethanoic acid, so this is going to be the R. Okay, this is the R. So CH3, and then you have C double bond O, and then OH. And based on what I taught you earlier, okay, we know that, okay, when they form the ion, okay, when they form the ion, okay, they are going to actually, the negative charge is going to become attracted. Yeah, the electrons are going to move around to the O over there, and they are going to actually, the negative charge is going to be delocalized, okay, between the O, C, and O, at the carbon double bond O. Okay, because of that, this particular ion is more stable. Okay, if they are stable, they are going to form more of this. Okay, it means in that process, okay, when they form more of this, you are going to have more H plus. okay, you're going to have more H plus. And that is represented by the Ka value, the dissociation constant, yeah? So let's say 1.7 to 1.7, 10 times negative 5. 1.7 times 10 negative 5. Okay, if you look at it. Now, what will happen, okay, if I have chloro over there? Okay, what will happen if I put the chloro over there? So if you have, let's say, chloroethanoic acid. Okay, so here is all hydrogen. So now I put chloroethanoic acid. So I have ethanoate ion, okay, and then I have CHH, and then one of it I put Cl. Okay, now we know, okay, that, okay, the electrons, okay, they are going to be delocalized over here. They are going to be pulled by the oxygen, yeah, they are going to become delocalized, okay, but we know the Cl, okay, Frederick, Cl is electron withdrawing or electron donating?
Donating.
Check properly. Okay, do remember this one, this problem will come. Yeah, I expected this problem. Okay, now this problem will come because, okay, you might get confused, okay, with the benzene. Yeah, benzene, when you look at benzene, when the Cl is attached, yeah, Cl has tendency to bring the lone pair of electron to go and overlap with the benzene ring. Yeah, but we are not talking about benzene over here. Generally, Cl, okay, is more electronegative, and they are generally electron withdrawing group. We are not talking into the context of benzene. Okay, I hope this is clear. Frederick, is it okay? Understand?
Yeah.
Yeah. So when it comes to benzene, yes, okay, we say chlorine Br is electron donating, yeah, because of the stabilization. But this one, we are not talking about anything to do with arenes yet, yeah. So just normal, yeah. In normal condition, yeah, they are also electron withdrawing. Okay, when they withdraw the electron, okay, when they withdraw the electron, what can you say about the charge density over there, Ryan? Less or more in comparison with the earlier one?
More.
You see, okay, the amount of charge over here and the amount of charge over here is the same, but someone is pulling that side. Okay, Cl is pulling, so it means that the charge is supposed to be reduced, right? Okay, because it's pulling. Okay, it's pulling, so it means that, okay, what will happen over here, okay, when they become, okay, predict what will happen, okay, they are going to become, okay, this is going to be, the charge is going to become less, okay, compared to the earlier one. Okay, when the charge become less, okay, we know that the tendency to they don't actually react. Okay, they don't react, so it means they have tendency to form more, okay, over here. So it means the H plus is there. Of course, you will have that. Okay, whether how more, yeah, because you are going to actually decrease more, okay, the charge density. It means tendency to form is going to be maybe a little bit more compared to here. Okay, a little bit more. Okay, so what happens? Okay, the H plus will be more compared to the H plus over here. This H plus will be more. Okay, why? Because the charge density is being reduced more. Okay, so that will make your Ka, if your Ka earlier is 1.7 times 10 negative 5, okay, the Ka now is going to become more, yeah, because you are going to actually give more H plus, okay, it should be more than 1.7 times 10 negative 5, okay, let's see, 1.3 times 10 negative 3, more, okay, and you can use the same concept if you have another Cl. Okay, you have another Cl over there. Of course, they are going to take more negative over there. This is going to become further down. Okay, so this is going to be more some more. Okay, and you can see that the Ka, okay, is going to decrease, become more. Yeah, if you have another Cl, you have more. Yeah, so it means that if you have electron withdrawing group attached, okay, if you have electron withdrawing group attached to that carboxylic acid, yeah, it means your acidity will increase. Okay, so in summary, what does it mean? Electron withdrawing group, okay, will further weaken the OH. Yeah, so that one is going to be the conclusion. Yeah, so it means that the H plus, okay, is going to be broken easily. Yeah, the H plus is going to be broken easily, okay, to become the undissociated acid. Yeah, so the okay, sorry, the H bond between the OH bond, the H will be dissociated more, yeah, when it is added to Cl, yeah, when it's added to Cl. Now, electron withdrawing groups extend the delocalization. It means they are going to extend the delocalization of the negative charge. It means more delocalization, yeah, further increasing the stability of the ion. Okay, this ion, the more Cl it comes, okay, the stability will be more. Okay, that is another conclusion that we need to add over here. Okay, stability will be more. Okay, so making it less likely to bond with the H plus. Similar to what we have learned for phenol. Yeah, so if you look over here in terms of diagram, okay, we know that this is going to be electron donating group. Okay, we know this is electron donating group. So we know that if, let's say, oxygen, yeah, they are going to actually bring the electron towards that side, and then if they form the ion, yeah, it will become delocalized. Yeah, delocalized, and when they form the negative ion over there, okay, this negative ion, because of the electron donating group, yeah, the negative ion is more. Yeah, if the negative ion is more, okay, what does it mean? They are going to be the H plus and the ion, they can react. Okay, if they can react, okay, it means that tendency to go to the backward reaction is more. Yeah, so they are not going to give you a lot of H plus. Yeah, so this one, okay, they don't give you a lot of H plus, but the moment that you have the Cl, one Cl group over there, yeah, you are going to have, okay, the negative charge to become starting to decrease. Yeah, so when they start to decrease, okay, they are going to further weaken the bond, okay, making this particular ion, okay, to become more stable. Okay, they become more stable. Okay, so when they become more stable, yeah, of course, okay, more delocalization. Yeah, if you have more delocalization, they are not going to react, okay, that much. Okay, so if they are not reacting that much, it means they have tendency to go and give you more H plus. Okay, and this tendency to give you more H plus increases the moment you have a lot of Cl. Okay, this will break easily. Yeah, this will break much more easily, yeah, compared to the others. Okay, why? Because they are going to be electron withdrawing groups. Okay, so here, okay, they say that ethanoic acid is the weakest. Okay, but okay, if you look at the moment you add the Cl over there, okay, then they are going to become a better acid. Yeah, better acid, where they are going to give you more H plus. Okay, I hope you can understand this. Okay, so here, if I put a question over here, place following acid in order of strength. Okay, starting with the strongest acid. How do we define a strong acid? Yeah, or how do we define acid? Yeah, so basically acid is going to be, strong acid means ability to dissociate. So in this case, we are talking about weak acid, so we are looking at Ka. So it means we have to look at which one has the biggest Ka. Yeah, which one has the biggest Ka, which one can dissociate more, yeah, or dissociate easily. Okay, when I look at it, okay, the moment I look at it, I know that this one will dissociate more. Yeah, why? Okay, because, okay, if you have C double bond O OH and then attached to C, there are 2 Cl, okay, and then 1 CH3. Okay, and this one is R group, okay, electron donating. Yeah, and then here is only going to be 1 Cl, okay, 1 Cl and then 1 CH3. So this has more. Okay, if you have more Cl, okay, what does it tell us? Okay, we know that the presence of the oxygen is going to withdraw the electron over there. So when they form this ion CH3, C, Cl, Cl, C, double bond O minus ion, yeah, there is going to be a delocalization of the electrons, okay, making it more stable, yeah. But this delocalization will be extended because this is also electron withdrawing, yeah, they are going to extend. So it means that the negative charge over here is going to become less compared to the rest. Okay, so it means that if you have the H plus over there, yeah, which is from the earlier part, okay, it is not going to be bonded. Okay, it's not going to be bonded because it's going to be more stable. Okay, this is more stable. Okay, what does it mean now? Okay, because not bonded, they are not going to give you the reverse direction. They are going to give you the forward direction. Okay, when they have the forward direction, yeah, it means that they are forming a lot of H plus. Okay, that's the reason why the Ka is more. Yeah, Ka is more compared to the rest. Okay, so explain why. Okay, ethanoic acid, yeah, in this case this one, yeah, I already explained, so you can read, yeah, you can read. Okay, but here they are asking, okay, why ethanoic acid is a stronger acid than ethanol. Okay, now we are comparing carboxylic acid and ethanol. Yeah, this one we already learned about carboxylic acid and ethanol. Yeah, so why carboxylic acid is stronger? Okay, you need to talk about the presence of this C double bond O minus, and then you just need to explain about, okay, this one will actually withdraw the electron more, okay, compared to ethanoic acid, compared to ethanol, because ethanol, okay, the C2H5OH, okay, this one is going to be electron donating this part, yeah. So that is going to be, this is going to actually increase, okay, this is going to increase the strength of OH, okay, but this is going to actually decrease the strength, the bond strength of OH, making it, okay, easier for this bond to be broken. Yeah, so this one you can read, you can see here, electron withdrawing carbonyl group, okay, this is going to be the C double bond O, weakens the OH, okay, making it more likely to lose the H plus, okay, and then the delocalization of the electrons, okay, they also stabilizes the ethanoic ion. Therefore, okay, this is not possible for ethoxide anion, yeah, because the ethoxide, they are not going to have any delocalization because they are going to actually give electron donating, yeah, it's electron donating. So this one you read, okay. Now predict which one will be a stronger acid, yeah, methanoic acid or ethanoic acid. So let's see, okay, let's see whether anyone can actually, you guys can predict this or not. Methanoic acid and you have ethanoic. So Sharon, can you predict which one is a stronger acid? Or I'll guide you, yeah. Okay, can you see this part, the H over here and then CH3? Can you tell me which one is a electron donating group?
Is it CH3?
CH3 is electron withdrawing or donating?
Donating.
Yes. Okay, CH3 is an electron donating group. Okay, the rest, okay, you see that they are going to the same thing, the electron, okay, they are going to become delocalized here, delocalized over here. Okay, so if they form the ion, okay, they are going to form O minus plus H plus. They are going to form CH3, C double bond O, O minus, and H plus. Okay, but when they look at the charge over here, and the charge over here, okay, we know that this is going to be electron donating. Yeah, they are electron donating. So even though there is delocalization, yeah, even though there is delocalization of electron, okay, this delocalization, because of the CH3, they are going to make the charge over here to become higher. Yeah, so when that charge become higher, okay, what happens? The tendency of this and this to join is more. Yeah, so when the tendency to join is more, okay, they are going to join and give you this. Okay, it means that, okay, it will favor the backward reaction. Yeah, it will favor the backward reaction. So it means that the H plus will become less. Okay, but here, okay, it's going to be like normal H plus lah, if you just put it in that way. Okay, normal H plus, this one become H plus is less. Okay, when the this one, because of H plus is more compared to that. Yeah, so this is going to be a better weak acid. Okay, better weak acid. So it means the Ka over here should be more. Yeah, so if you look over here, okay, methanoic acid will be a stronger acid. Okay, methanoic